Greetings, ladies and gentlemen. This is 11.4. We're looking at how to graph polar coordinate equations. The first thing we're going to learn about is how polar coordinate has symmetry in the Cartesian xy plane. All right, so we have three types of symmetry we're going to look at. First, it's um, about the x-axis, about the y-axis, and about the origin. Right. So they are pretty similar to what we have seen with regular Cartesian functions having symmetry, right? Above about the x-axis, y-axis, or the origin, right? But in this case, we are actually looking at their coordinates in terms of symmetry. Now, how many ways can we write symmetries? All right. So for part A, right, if the point is r theta and it has symmetry about the x-axis, then it's going to have the point r and negative theta, or negative r and pi minus theta. Right. So all these there are just different way of writing the same point. Right. And same thing with part B about the y-axis. Right. We can see the graph here. Right. The original point r theta, and then the coordinates for their symmetries. And again, we have two of them. Right. Just different ways of writing the same point. Right. And then part C is when you have symmetry about the origin, then the point negative r theta, or r and theta plus pi will be the same point, symmetric to the original point r theta. Okay, so here we're just looking at some of the symmetries um, in terms of polar coordinates. All right? And also we have, if it's symmetric about the x-axis and origin, then it implies it's symmetric with the about the y-axis. Right, and also it implies the other way as well. If you have symmetry about the x-axis and the y-axis, it also implies it has symmetry about the origin. Right, so if you have two of them at the same time, then it's going to be equal to the third one. Right, so let's say if you are symmetric about the about y-axis and the origin, then it automatically means it's symmetric about the x-axis. Now, next, to find the slope of the curve uh, r equal to f theta, which is in the form of polar equation, it's not as easy as just take the derivative of r with respect to theta. Right? We have this formula we have to use, because when we look at the slope of a tangent line, it's actually in Cartesian. It's not going to be in polar. Right? So in this case, we need to use this formula to find the slope, or dy dx in this case. Yeah. In the textbook, it shows why we cannot just use df d theta to represent the slope. Right? But if you're interested, you can take a look at that. But this is the formula we're going to use if we want to find the slope of the tangent line. All right. So example one, we're going to try to graph r equals 1 minus cosine theta. Right. This is a polar equation. Now, before we actually start on picking out some points and plotting the points, let's see if we have any symmetry on this equation. Right. So suppose that r theta is on the graph. Right. What that means is this equation is going to be true. Right. R is equal to 1 minus cosine theta, right? R and theta for some R and some theta, that's on the line, right? And what we know is that cosine is actually an even function, right? So what we can do is this. We can, instead of using theta, we can use negative sine theta. Negative theta, not negative sine theta, negative theta, right? And they are the same thing, right? Cosine theta and cosine of negative theta, they are the same thing. And what this equation tells us that is that r and negative theta is also on the point, is also on the line, on the graph, right? So what tells us is that if r theta is on the graph, then r and negative theta is also on the graph. Right? And what type of symmetry is this? Let's go up and look, right? R theta and R negative theta, right? It's going to be the first one, right? R theta is on the line. That means R and negative theta is on the line. So it has symmetry about the x-axis, right? So therefore, symmetry about the x-axis. Right. So what that tells us is that when we are going to graph, all we need to worry about is the top side of the x-axis, right? X and Y, right? Whatever we have on the top and top side of the x-axis, we can just mirror it down to the bottom, right? And then what represents the top side, right? We only want this side, right? So we can understand this as from 0 to pi, right? And whatever it is up here, it's going to mirror to below the x-axis, right? So all we need to do is graph theta from 0 to pi. All right, and let's go ahead and do that. Let's start building a table of solution first, right? So we have theta and r, which is 1 minus cosine theta. All right, so build a table of solution like that. And our goal is just to go from 0 to pi, right? So let's do 0, let's say pi over 3, pi over 2, 2 pi over 3, and then pi. Okay, and let's just fill in this pretty fast. The first one is 1 minus 1, which is 0. 1 minus 1 half. Cosine of pi over 3 is 1 half, 0. And pi over 2, it's 1 minus 0, which is 1. 2 pi over 3, 1 minus negative 1 half, which is 3 over 2. And then at pi, we have 1 minus negative 1, which is 2. Now, the previous one is 3 over 2. All right. So we have all the thetas from 0 to pi above the x-axis, right? Positive rotation, which is above the x-axis. And the corresponding radius, r. Oh, sorry. For pi over 3, it's not 0. It's 1 minus 1. That's 1 half. All right, and let's see how we can graph this. All right, so I'm going to write down the ordered pairs right down here, so it's a little easier to graph. 0, 0, pi over 3, 1 half, pi over 2 and 1, 2 pi over 3 and 3 halves, and pi and 2. All right, let's go ahead and try to plot these 5 points. And these are in polar coordinates, right? Let's do that. All right. First, 0, 0. So 0 degree and 0 radius. So if the radius is 0, it's always here. Right? Let's actually name these points. Let's call them A, B, C, D, and E. All right. So this orange point at the pole, that's your point A. All right. And next we have 1 half, pi over 3 and 1 half. All right. So pi over 3, let's say it's about here, right? And then let's label these 1, 2, 1, 2. So pi over 6, pi over 3 and 1 half, that's probably going to be around here, right? Just give it a rough estimate. Let's say B. All right. Next, we have pi over 2 and 1. All right, pi over 2, that's very easy, 90 degrees. All right, so on the y-axis and 1. All right, there's your point C. And then D, we're looking at 2 pi over 3. So, oops, that's trying to graph 2 pi over 3. All right, that's good enough. All right, 2 pi over 3 and 3 halves. So a little bit more than 1. That's about here. All right, that's D. And then E, it's pi and 2. All right, so pi, we're looking at the negative side of the x-axis, and 2. So 1, 2. Let's say about here. All right, so E. There you go. All right, so hopefully you can see the pattern we have here. We started at A, so we're trying to connect the dots A, B, C, D, and E, right, in increasing order of theta, yeah? And then trying to graph it with a smooth curve. Right, so it will be like this. Go up to B. All right, and then down like that. Okay. It shouldn't be like a. Let me make it a little smoother, like that. There you go. All right. So this is the top side of our graph, right? And to graph the bottom side, there are a few ways, right? Of course, you can just copy the graph and then do it in reverse, or if you want to make it a little more accurate, right, we can always plot those symmetric points. Just give it a rough sketch, right? Somewhere maybe here, right? Right. And that looks good. And then finish your graph, circling back. Actually, this is a little too low, right? And then you want to circle back like this. All right, all right. It's not too bad. Okay, there you go. And yeah, there you go. That's the graph of 1 minus cosine theta. Okay. So pretty straightforward, right? Very similar to just graphing any function. Right? You pick some point. If you know about the symmetry, then you know it's easy to work with symmetry. And basically, most of the polar equations, they are going to have symmetries in some form, especially if you have cosine and sine or tangent in there, right? Cosine, sine, cosine, tangent, they all have a certain type of symmetry with it. So you can definitely find one type of symmetry to work with. All right. And then you graph the top part and then just copy down the bottom part. All right. So let's look at a few more. I'm sorry to I forgot to mention. So we have the rotation, which is in this direction, right? In the positive theta direction. Let me just make a little arrows on that. All right, there you go. All right, so let's look at our second example. Example 2, we're looking at r squared is equal to 4 cosine. So first things first, right? We still want to check for any symmetry, right? So suppose r theta is on the graph. Then we can start with r squared is equal to 4 cosine theta. Right? And we know from earlier that r squared is equal to also 4 cosine negative theta, right? So r and negative theta is also on the graph, right? Which means it's going to have symmetry about the x-axis, right? But that's not it, right? We also can work with the r, right? For example, I can rewrite that as negative r squared, right? And that's the same thing, right? So that means negative r and theta is also on the graph, right? And if negative r and theta is on the graph, then that is origin symmetry, right? And we know that if we have two of them at the same time, then that implies we also have symmetry about the y-axis, y-axis symmetry. Right? So this is a very nice case, right? Let me show you why. Let's say I figure out the graph in just quadrant one. Let's say it looks like this, like that. That's a bad one. Let's say it looks like that. Okay. And then we know that's symmetric to x-axis, right? So we can draw it like that. And then also symmetric to the y-axis, right? So we can draw the mirror image on the right-hand side to the left-hand side. So we'll have this like that, right? No, but this is not exactly what the graph is. We'll have to figure it out what the detail is later. But yeah, that's basically what we're going to be doing. Right? If you have all types of symmetry, all you need to worry about is just one part, right? One quadrant of the graph, and then you can copy the rest. All right, so let's take a look at how we can pick some points. So we know r square is equal to 4 cosine theta. Now we can't actually just graph this because we'll get two values of r. So if we take the square root of r, we get r is equal to plus or minus 2 times the square root of cosine. Okay. All right. So we will have plus and minus. Now in this case, we actually want to include some points in the first quadrant, right? So for example, we can go from 0 to pi over 2, right, in the first quadrant. Right? So let's build the table first. And r is plus minus 2 cosine theta. Now the plus and minus part will actually give us 2 points, right? So let's just worry about the positive part first. All right, so let's see. We want to go from 0 to pi over 2. All right, so let's see. Let's do 0, pi over 6, pi over 4, pi over 3, and then pi over 2. All right, so just all the special ink. All right. Okay. What I'm going to do now, I'm just going to punch that into the calculator, right, and we'll see what we have. All right, so this is going to be 2, about 1.9, about 1.7, about 1.4, and then 0. All right, so let's plot these 4 points. Okay. All right, so 0 and 2. 1, 2. 1, 2. All right. Notice I'm just focusing on the first quadrant, right? So 0, 2, right here. Pi over 6, 1.9. That's about, say, here, right? And then pi over 4, 1.7. Let's say 1.7. Say it's about here. All right. And then pi over 3. Oops. Pi over 3, 1.4. So it's a little shorter, maybe about here. No, a little higher, I think. Maybe here. Okay, and then pi over 2, 0, so back to the origin. When r is 0, you're always back to the origin. Right? So we see this shape like the top half of an egg, right? And let's graph it like that. Okay, that's really bad. Let me try that again. Okay, there you go. And then we know that the rotation is this. Now to finish the other part, right? All we need to do is we can use the symmetric property of this equation, right? So we can do the half side. Oops. to the half side like this, right? Complete the egg. And then we can just flip the egg to the left hand side, and then we will have an egg on the left hand side. Like that. Okay. I know it's not symmetric just by the looks of it, right? But I tried the best I can, right? So another thing that we need to worry about is we only know the rotation of quadrant one, right? What about the others, right? Let's say when we rotate from here, from 0 to pi over 2, that looks like this, right? We're in this rotation, right? But what happens when we hit 0, and then which one do we go? Do we go to the left hand side or do we go to the right hand side, right? So that's something we have to figure out. And to do that, we can just pick out some other points other than the ones that we have picked, right? And then we'll see what we have, right? For example, let's do this. The graph that we got in quadrant one came from taking the positive form of two radical cosine, right? So let's see what happens if we take negative, right? If you make this negative, then all these values will be negative, right? So in that case, we will be we'll have 0.0 negative 2, which is right here, right? And pi over 6 negative 1.9, pi over 6 negative 1.9, that will be here. Pi over 4 negative 1.7, somewhere around here, and then so on, right? So by taking the negative side, we know the rotation will give us this part. Right? So that takes care of some of it. Now, we don't know about the rotation of the other two, right? So there are a few ways to think about it. First is just by looking at um, the two parts that we know the rotation of. For example, let's look at quadrant one. Now, quadrant one, it rotates back to the pole, right? The origin, right? Now, we only had two possibilities. Either it goes down to quadrant four, or it cross over to the left hand side to quadrant three, right? But we know that quadrant three actually has opposite rotation and of the quadrant one, right? They are going towards each other, right? So the only possibility to finish this is by rotating it backwards, right? Rotating around the circle on the right hand side, and then on the left hand side, it rotates on the circle on the left hand side, right? Now you might think, okay, maybe we can try to pick out some other points, right? If we pick anything that's greater than pi over 2, then cosine, let's say pi, right? Cosine pi is negative 1, and we will have negative 1 in the square root, which will not make sense, right? So we can only pick angles, thetas in quadrant 1 and 4, right, where cosine stays positive. And to do that, we can also pick thetas from negative pi over 2 to 0, right, which is in quadrant 4. Right? We don't want to go into the 3 pi over 2 to 2 pi. Of course, they are the same thing, but to keep the things close to our original theta, which is 0 to pi over 2, we are going to use negative 2 pi to 0. Right? If you pick those points, you will get some values as well. Right? Let me show you an example. Let's say theta is negative pi over 2, then r is equal to 2 times cosine of negative pi over 2, which is still 0, right? That means when theta is negative pi over 2, you are also back at 0. But that actually doesn't tell us anything about the rotation. So let's pick another one. Let's say um, negative pi over 6, right? And r is 2 times cosine of negative pi over 6. And we know cosine is even So this is actually equal to 2 times cosine of pi over 6. And from earlier, we know that this is equal to 1.9, right? So we have negative pi over 6 and 1.9, which is right, pi over 6, 1.9, which is right here, right? And then as you increase the angle, oh, sorry, not here. Pi over 6 is right here. Right? This is negative pi over 6 and 1.9, right? And then this is where negative pi over 2 and 0 is. Right? So as you increase theta, it's going to go that way. You're going to get to this point, this point, this point. Oh, no. Right here and here. Right? And then you're going to hit 0 and 1 again. So on the left-hand side, on the right-hand side, this circle, it's actually the positive part of r equal to 2 square root cosine theta, right? Where theta is between negative pi over 2 and pi over 2. Right, on the left-hand side, we have r is equal to negative 2 cosine theta, and theta is as well from negative pi over 2 to pi over 2. Okay. And if you want a nicer picture, there's a picture in the textbook on page 678. 87, 687. Right. So feel free to take a look at the better picture, and then they have the table with all the positive and negative sign worked out. Right. So that's another way of graphing a nice picture with all the symmetry, right? You graph the first quadrant, and then you just copy it, the mirror images to everywhere else. All right. And another way to graph the polar equation is by converting a graph from r theta to the xy plane. Right. So first step is we want to graph the function r equals to some function of theta in the Cartesian r theta plane. Now that might sound a little weird, right? But it's actually pretty straightforward. Instead of x and y axis, you have theta and r. All right, that's it. All right, so it's like you're looking at theta as your x and r is your y value. All right, so let's go ahead and attempt to do that. Now, there are two ways to do this. The first way is actually covered in the textbook, but I really don't like that method, so I'm going to go with the easier one. We have r squared is equal to sine of 2 theta. And when you take square root on both sides, you get r is equal to plus or minus the square root of sine 2 theta. Right. So our goal is we're going to graph this on the plane. So both plus and minus. Let's do the plus part first, right? So r is equal to square root of sine 2 theta. And then we are going to build a table. Right? We have our theta and r. So let's just pick some points. All right. From 0 to 2 pi. Right? One period. Oh, actually, since it's sine 2 pi, if we go from 0 to 2 pi, that will be 2 periods, but that's fine. All right, so let's say 0, pi over 4, pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, 7 pi over 4, and then 2 pi. Okay, that's pretty long, but that's good enough. All right, sine of 0 to 0, sine of pi over 2, pi over 4 times 2, that's 1, right? And sine of 2 times pi over 2, that's sine of pi, which is 0. Sine of 3 pi over 2, which is negative 1, right? But square root of negative 1 is imaginary, right? So does not exist. All right, and sine of 2 pi, it's 0. Sine of 5 pi over 4, that's sine of 5 pi over 2, same thing as pi over 2, right? So that's 1, right? 3 pi over sine of 3 pi is 0. Sine of 7 pi over 2, that's the same thing as 3 pi over 2. That's going to be negative square root of negative 1, right? And then sine of 2 pi or 4 pi, that's going to be 0. So you'll see that actually we have a few unknowns, but not a big deal. Let's go ahead and graph it first. All right. Actually, I want to do a different one. Since we're going to look at 0 to 2 pi, I think this will work a little better. Okay, so the horizontal axis is now theta, and the vertical axis is r. All right, let's plot these points. 0, 0. So let's say that's 2 pi, pi over 2, pi, 2 pi, and 3 pi over 2. All right, so 0, 0, pi over 4 and 1, right here. Pi over 2, 0, right? And 3 pi over 4 is unknown, so we don't have to graph it. At pi, it's 0. 5 pi over 4 is 1, right? So that's right here. And then 3 pi over 2 is 0. Nothing between 3 pi over 2 and 2 pi, and then 2 pi is 0. Okay. All right, so we know that actually between pi over 2 and pi, since sine of 2 pi is going to be negative in here, we actually don't have anything between pi over 2 and pi. Same thing between 3 pi over 2 and 2 pi, because r is negative. No, not r. Sine of 2 pi, 2 theta is negative. Right? That means we will end up with a negative number in the square root if we pick any values between pi over 2 and pi, or 3 pi over 2 and 2 pi. So there's nothing in these two intervals. Right? All right. So for what we have, 0 to 2 pi, right, we'll have a graph like this, right? Kind of like the sine graph, right? Except no negative parts. All right. So that's a positive one. And to graph the negative one, right, all we need to do is just add negative sign to all the values that we have in the table, right? So 1 becomes negative 1, 0 will stay 0, right? And then for negative r, right? Or I should say negative sine 2 theta, right? All we need to do is change all the 1s to negative 1, right? So the graph will be actually symmetric to this. It's just going to be on the bottom side like that. Okay. So you can see that it actually repeats himself, right? These two are the same thing, right? And all we need to do is we just need to convert this to the polar coordinates, right? We want to convert that to the Cartesian XY axis. And I'll show you how to do that as well. Okay, there we go. Now, what we're going to do is we're just going to pick some points, right? Let's say pick this point and that point. And also this one right here. All right, so the first thing we're going to look at is the zeros, right? So we know that the first 0 happens here, right? First r equal to 0. And the second r equal to 0 is here. Right. So that means when theta is 0, we're going to start at the pole. We're going to start right here when theta is 0. And we're going to come back to r equal to 0 when theta is pi over 2. All right, so that means during this time, going from theta equal to 0 to pi over 2, this is one loop. All right, we're going to have a loop coming back to the pole. Right, and what happens between these loop when theta goes from 0 to pi over 2? It increased up to 1, right? Where the highest point is 1, it happens at pi over 4, right? So at pi over 4, there is a 1 up here. Okay, so it's going to go out and loop back like this. That's not a really good one. Let me try again. Okay, that's not a good one either. But you get the idea. It's going from 0 to pi over 2 is going to loop back to the pole. Okay, one last try. Yeah, that's much better, right? So this part is going from theta equal to 0 to pi over 2. Right? But we also see that instead of looping from the positive one, in the negative side, we also go down to -1 from 0 to pi over 2. Right? So r is going to become negative r. Right? So we know that negative r and theta is also on the graph. Right? So instead of using a positive radius from 0 to pi over 2, we're going to do negative. So when theta is pi over 4 and -1, we actually have a point right here, right? Pi over 4 and -1. That's when r is negative. That's this point right here. Okay. And then the same thing is going to loop from 0 to pi over 2 with negative radius. And that looks like this. Okay. There you go. All right. And that's just from 0 to pi over 2, right? But actually, it's the same thing from pi to 3 pi over 2 as well. It's just going to go through these two loops over and over again, no matter what your theta is. Now, of course, we don't have theta between pi over 2 and pi because that gives us a negative value in the square root. Right? So these 2 points, let's do a quick reference. These 2 points, like that, it's saying something about these 2 points, right? And this one that's on the bottom, it's talking about the pi over 4 and -1, right? This point up here is pi over 4 and -1. And so we have to consider both the positive and negative square root when we are graphing the polar equation. It's not like we're regular Cartesian equation, we cannot graph them in the same function, but in polar, we can have something like this, okay, where it just gives you 2 loops. Right? Another thing, whenever r goes back to 0, like what happens at 0 and pi over 2 in here, this represents a loop because it's going to go back to the pole, right? So every time you hit the pole, it's going to represent a loop. Okay, let's see. Another thing, I forgot to mention this earlier. The second loop, where we go from pi to 3 pi over 2, they actually have opposite point of direction, like this, right? So these 2 points represent the upper loop in quadrant 1. whereas this point represent the loop in quadrant 3, right? So they are opposite of each other. You can actually finish the graph with just one function looking like this. All right, for example, if we look at this point right here, this is 5 pi over 4 and 1, which will give you this point as well, right? This is 5 pi over 4 and 1, right? So same point as pi over 4 and -1. So it doesn't matter if you look at the positive one or the negative one, right? Positive radical sine 2 pi or negative radical sine 2 pi. You actually get the same graph over and over again. And let me show you on decimals where we can get a nicer look at these graphs. Right, so this one is negative radical 2 pi, but if I take away the negative, I still get the same thing, right? It's just that the starting point and the loop, or the way that you will complete the graph, is a little different. Right? Let me go back to our OneNote here, and I'll show you. All right. So we know that the graph looks like this, right? But for the positive part, it has the rotation of this. Right, it's gonna start here, come back down, stop, right? And then when it hits pi again, and then going to 3 pi over 2, right? It's gonna go like this again, right? Whereas, so we do this part first and then second, right? But if you're looking at negative radical sine 2 theta, it's a little different, right? We're going to look at the negative part first, right? So it's gonna go like this first, right? And then take care of the upper part later, like that. Okay, so if it's negative, we do the bottom part first, and then the top part second. Oh no, they are still the same thing, right? It's just gonna loop over these two things over and over again. Right? And all we worry about is the rotation, right? We don't care about where you start. Doesn't matter if it's positive or negative. Okay, so that's it. And decimals, right? There's decimals.com, right? If you Google decimals polar, then you will be able to get the calculator that will allow you to graph polar equation on decimals. Or you can always use Wolfram Alpha to graph a polar equation that way. Okay, so that's it for today. 11.4, graphing polar. Thank you guys very much. See you next time.